Here's our truck going up an incline, let's say, of 10 degrees. And again, we'll have a coefficient of static friction of 0.170. And let's assume that our crate has a mass of 15 kilograms. That way we'll be able to just stick the numbers in and find all the numbers at the end. Let's draw a free body diagram. I've drawn it over here. What do we have? We have the weight, again, straight down. We've got the normal force, perpendicular to the incline. And if the truck is accelerating up the incline, the force that will be accelerating the crate will be, again, the static frictional force. So let's figure out what's the maximum rate that the truck can accelerate. So we'll put it at Fs max, the maximum amount of force that we can apply to the crate to accelerate it up the incline. Again, we'll break this down into x and y components. We'll define x as along the incline, and in this case we'll say up the incline. The truck is going up the incline. Y perpendicular to the incline. To do that, we're using these coordinates, we're going to have to break our weight down into x and y components. Again, the x component down the incline this time will be negative mg sine theta. The y component, again, into the incline in the negative y direction will be mg cos theta. Well, that means then that our normal force is going to be mg cos theta, like it usually is on an incline. So what is our value for Fs max? Fs max is mu s times the normal force, or mu s mg cos theta. Sticking our numbers in, mu s 0.170, m 15 kilograms, g 9.8, cos 10 degrees. What do we get? We get a maximum static frictional force of 24.6 newtons. What's working against that in the x direction? Well, it's the weight, the component of the weight down the incline, mg sine theta. So what's that? Well, mg sine theta is 15 kilograms, 9.8 sine 10. Multiply that. What do we get? 25.5 newtons. Well, what does that tell us? The force down the incline due to the weight is larger than the maximum static frictional force that we can apply. No matter what, this force down the incline is going to be larger than the force up the incline. There is no way that the mass can accelerate up the incline. If the truck starts to move, that crate is going to accelerate, or is going to slide off the truck. The truck will accelerate out from underneath the crate. There's no way for that truck to make it up the hill and keep that crate on the back of the truck. Well, let's take a look at another type of problem. This is going to involve another kind of force we haven't looked at before, called a tension force, but it's a very, very important type of problem. Tension is the type of force that is exerted anytime we have a string or a rope or a cable or a chain or something like that that is pulling between two things. The important thing to keep in mind is that if I pull on my right hand pulls on my left hand and I pull it this way, my left hand pulls back on my right hand. So again, Newton's third law, whatever force object 1 exerts on object 2 exerts on object 1. So the tension you can think of as basically a constant quantity through the entire string or rope or whatever. The other thing to think about is that what's the direction of the force? Can I pull my right hand in that direction with this string if it is extended vertically? No, there's no way I can pull on my hand in that direction unless I take the string over to this direction and pull on it this way. If the string is vertical, the only way that I can pull on my right hand is upward, and the only way I can pull on my left hand is downward. So the force acting in the string or the chain or the rope or whatever, the tension, always is along the line of the string or rope or whatever. So you know that if the string is this way, the force being exerted on this hand is right along the string that way. The force exerted on this hand is along the string up that way. Excellent. Let's try and apply that to a particular problem. Let's imagine that we've got some mass, maybe 321 kilograms, suspended from a rope or a cable or something like that from the ceiling. And then someone else has attached another cable onto this one, and over here pulls it over in this direction so that this mass is kind of swung over to one side. Let's see if we can analyze this problem and figure out what tensions must be in each of these three ropes in order for this to be held stationary. We'll assume that it's just stationary for the moment, so the acceleration is 0. What kind of tensions must be exerted in these three ropes in order for this to be held stationary? Let's stick some numbers in. Let's imagine that this rope makes a 10-degree angle with the vertical, and this rope makes an 80-degree angle with the vertical down here. How are these forces acting? The idea here is, let's imagine all of these forces acting at this point right here, where all of those forces come together. What direction do those forces act? Well, T1, remember, is pulling up that way, so T1 exerts a force in that direction, on this point. T2, pulling down that way, exerts a force down that way, in that direction. T3, pulling down here, pulls directly straight down. Those are the directions all acting at that point. Assuming that this is stationary, assuming there's no motion, what is the net force acting at that point, that little point where all those ropes come together? The net force has to be 0. That tells us that the vector T1 plus the vector T2 plus the vector T3 has to equal 0. T1 plus T2 plus T3 vectors must equal 0. In other words, the x components of all of these must equal 0, and the y components added together must equal 0. Well, that's how we can solve it. We can look at the sum of the x components, set it equal to 0, the sum of the y components, set it equal to 0. Here we've made the assumption that because the object is not moving, the object being that point right in the center, if the acceleration is 0, the net force has to be 0. All right, let's try that. Let's break this down into x and y components, x being horizontal, positive to the right, y being vertical, positive up. What are the x components? Well, we've got three forces. We need to look at the x component of each. But before we do that, let's just look at T3 just for a second. We know T3 is acting on the mass also. T3 is pulling on the mass up, and the weight is pulling on the mass down. So T3 must be exactly equal to the weight of that 321 kilogram mass. Well, we can figure out what that is. T3 is just mg, so T3 is 321 times 9.8, or 3,150 newtons. So we know T3. We can just put in that number anytime we want to use T3. What about the others? Well, let's look at the x components. First of all, what's the x components of all of these forces? Well, what's the x component of T2? The x component here, notice that's the side opposite that 80 degrees, so that's going to be T2 sine 80 degrees. The x component of T2 is T2 sine 80 degrees. What about the x component of T3? Well, T3 is exactly in the y direction, so the x component is 0. What about the x component of T1? The x component of T1 is going to be this side, which is again opposite the 10 degrees. So it's going to be T1 sine 10, but notice T1 is pulling to the left, the x component is negative. So we have minus T1 sine 10 degrees equals 0. You can leave these in terms of sine 10, sine 80 if you want, and only put the numbers in at the very end, although I think for a lot of students it's probably easier to put the numbers in ahead of time. Sine 80 is 0.895, so we've got 0.895 T2 minus sine 10 is 0.174, T1 equals 0. Now what about the y components? The y components we have, first of all, the y component of T1, that is the adjacent side, so that's going to be T1 cos 10 degrees, that is in the positive direction. So we have T1 cos 10 degrees. The y component of T2, that is the opposite side, over here. That is the adjacent side, so that's going to be T2 cosine 80 degrees, but it's in the negative direction. So we have minus T2 cos 80 degrees. And then T3 is pulling down, so we've got minus 3150 newtons, and all of that must equal 0. Again, we can put the numbers in there, but just let's think about this for a second. How are we going to go about solving these? We've got an equation that involves both T1 and T2, and an equation that involves both T1 and T2. Well, I think probably the easiest thing to do is to take maybe this equation, bring this over to the other side, and solve for T2. T2 will equal something. And then take that something and put it in here for T2. Then we'll have just one equation that only involves T1, and we can solve that for T1, and then come back here and solve that for T2. Well, let's try that. From this equation, we'll bring the 0.174 T1 to the other side and divide both sides by 0.985. That leaves us with T2 is 0.174 T1 divided by 0.985, or 0.177 times T1. Now from the second equation, putting the numbers in, cos 10 is 0.985 and cos 80 is 0.174. So we have 0.985 T1 minus 0.174 T2, and I brought the 3150 newtons over to the other side, so equals 3150 newtons. Now let's take this quantity. T2 is equal to 0.177 T1. I'm going to rewrite this second equation, but I'm going to put in this for T2. So we have 0.985 T1 minus 0.174, but instead of T2, I'm going to put in 0.177 T1, and that equals 3150 newtons. Now, multiplying this out, look, we've got a T1 and a T1. I can divide T1 from both sides. So that is equal to 0.985 minus 0.174 times 0.177. All of that times T1 equals 3150. Multiplying this all out, we get 0.954 times T1 is 3150 newtons. Dividing both sides by 0.954, T1 is 3150 newtons divided by 0.954, or T1 is, and I had to write this in scientific notation to get my 3 sig figs, 3.30 times 10 to the third newtons. Whew, that was a bit of algebra, a bit of mathematics there, but I hope it made sense. And you might go through it a little more slowly, do it on your own, and see if you can make sure to get all of those things to work out. And hopefully that will give you the same answer. Now, let's come back up here. We know that T2 is 0.177 times T1. So if we take this value here for T1 and put it in here for T1, multiply by 0.177, we'll find T2, and T2 is then 584 newtons. Very, very good. By applying Newton's law, F equals ma, to this central point here, because we know we had all of these forces, T1, T2, T3, all acting together at that net point, and it's not moving, we know that the net force acting at that point had to be 0. In other words, the vector T1 plus the vector T2 plus the vector T3 had to be 0. If that's true, if a vector sum is 0, the x components have to be 0, the sum of the x components have to be 0, the sum of the y components have to be 0. Have to add all up to 0. By doing all that, we could figure out what those magnitudes T1, T2, T3 had to be. Very, very good. Let's take a look at one more kind of problem. This will be a problem that if you're in the lab and you do this experiment with the Atwood machine, you'll see this in lab.